All right. This one here is the one where we start doing proper binary attacks. And the important thing here is you'll learn how to use the debugger and how to write the attack in Python and why you need to do that. So this uses this vulnerable program, pwd.c. Let me clear this and cat pwd.c. Okay, so this one works like this. Main is down here. So it's going to, you're going to execute it, and it's going to call the test PW function, and that will return, if it returns 1, it'll say fail, otherwise you'd win. And this function is going to read a password from the user, which can only be up to 10 characters long, and then it's going to always return 1. So no password is correct, you will always fail. And the point is there is a win function, but the logic of the program as written by the developer is there's no way to get to the win function, and we are going to find a magic password that gets us to the win function. All right, that's the point of this thing. It's the simplest, and we're going to allow the password that you read to be up to 50 characters, even though there's only 10 characters to store it, so that's how we're allowed to have the overflow. That's all this thing does. All right, and so just like before, we compile it for 32-bit code, and also install XXD, which we're going to use. It's a very handy way to test files, we'll see. All right, and so that made this file called pwd32. It's here. And if you use the file command on Linux, this is very handy. It tells you about a file. This file is an ELF 32-bit executable. ELF is executable link format. That's Linux executables. Windows is PE, portable executable. So this thing will run on a 32-bit Linux system or on a 64-bit Linux system that has the multi-lib library installed. So I can run this thing, pwd32, and give it a password of like ABC, and then I fail. But if I give it longer passwords, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that works. But if I give it 2 more long ones, like maybe 20, then I get a segmentation fault. And this is what you want. The segmentation fault means you have tried to access memory that is not reserved for your use. And that's what we want. So the whole point of exploit development is this. Typically what you do is you have some software, you want to find flaws, so you fuzz it. You send random junk to the server until it crashes. Now you've found a denial of service attack. Now a properly running server, no matter what you send it, it will not stop, it will not crash, nothing bad will happen. It has appropriate tests to check the input and give you controlled error messages. If you can make it crash with an error like this, then it's vulnerable. And what I have now is a denial of service attack. The whole purpose of exploit development is to improve this into remote code execution, which is, of course, much more powerful than just a denial of service attack. So that's what we're going to do. In order to do it, you got to debug the code. By the way, here's another problem. All modern operating systems have address space layout randomization. Every time they run, they randomize the address of things. And you can see that here. The first time I ran it, the password was at this address. The next time I ran it, the password was at that address, CCE 7. Every time you run it, the password's at a random address. This is a modern defense. Every time you start a program, you randomly locate it in memory. That is to stop simple attacks like what we're doing. So for what we're doing, we want to turn that off. You can't turn it off in Windows, but you can turn it off in Linux. There's just a environment variable. So you have to do sudo su minus to move to root and be in the root environment. And if I have to give it my password, now I'm going to be root. Now I execute this command, which will put a 0 in this randomized VA space variable. And then I can exit from root. Now I'm back to my normal account of student. And now if I run that program, pwd32, give it a password of A, and just do that again and again, now it's always the same. D4F6, D4F6. That's what I want. This is the old-fashioned way all the machines were back in the days of Windows XP. Nobody thought of randomization at that time, and that's why these exploits all became very popular. So, and there are ways around it. The way to avoid this is a trampoline attack and other ones like that, but we'll get to those later. All right, so now that we got there, now we're going to debug the program. There are a lot of debuggers. I would just prefer to use the standard GDB. GDB is the ancient command line only debugger. There are people that attempt to make graphical debuggers on Linux, and as far as I can tell, they're all worthless. Some people love them, but GDB is the classic one. So to debug a program, use GDB, minus Q just makes it quiet. And then we're going to do PWD32. This is the GNU debugger. Now this is an incredibly powerful debugger. There are hundreds of commands. It can do anything, but we're only going to need about 10 of those commands, the simplest ones. We're only going to do the basic things here. So the first thing you can do is just list the program. Since I compiled with the -G switch, it connects the source code to the debugger. So you can even debug from source code, which is of course a lot easier than reading assembler. And that's what we're going to do here. So in fact, you can also list more. I could do 1 to 13. All right, and you see here, so here's the test PW path, and here's the win function. In fact, I could just do the whole thing if I go up to what, like 20 or 25. That should give me, there. There's my whole source code. Here's the main, here's the test PW, and here's the win where I want to go, but I'll never get there by running the logic the programmer wrote here. All right, so now what we're going to do is we're going to look at the overflow point. And we know the overflow is going to happen right here. This is where it reads something from the user that can be up to 50 characters long, and it puts it in something that only has room for 10. This is the interesting line, so that's line 8. So I'm going to put a break at line 9. So after this has happened, I'm going to stop and examine the contents of memory. So put a break at line 9. All right, now I run. It asks me for a password. I'm going to put in AAA, 8 characters. And now I have hit the breakpoint. Now I can examine the memory. And I'm going to do info registers for start. If your processor has these registers, which are little memory locations on the processor itself, which is what it uses to control flow. The most important one is the EIP. This is the address of the next instruction to be executed. And so right now it's in the test password routine. It's about to return, and this is where it is, 84 bytes into the test password routine. But the other important registers for us are ESP and EBP. When you call a subroutine in C, it allocates a certain amount of stack memory for this subroutine to use. And it goes from ESP as the top of that stack frame, and EBP is the bottom of that stack frame. And when it returns from a subroutine, it releases that memory for reuse. So this is the temporary storage location for in the test_PW routine. It goes from 4B0 to 4C8. It's not very big. And you can examine that with X, say 16X ESP. Whoops, I got to have a space, not a slash here. All right. And so, remember, it went from 4B0 to 4C8. So this is the stack frame for this process. And by the way, this is a little screwy to read, but it says B0 here. What that means is these are the bytes from B0 to B3. These are the ones from B4 to B7. These are the ones from B8 to BC, or BB, and this is BC to the end. These are 32-bit words, each 4 bytes long. And unfortunately, because it's Little Endian, this is B0, this is B1, B2, and B3 to make a 4-byte 32-bit integer. So it can get confusing. And here are the A's I put in. Capital A is 41, so there's 4 of them. Here's 2 more, and here's the other 2. So you read each one of these right to left, and then you go to the next one. So these are the 8 capital A's that I put in there, just sitting in memory. And remember, I did not have an overflow here. I only put in 8 A's, and there was room for 10. So this is operating normally. And what happens is, under normal operations, if you find the EBP, which is 4C8, that's here, the highlighted memory is the stack frame, and the last thing in the stack frame is the stored base pointer when you return, and this byte right here is the stored return pointer. So when it's done executing this routine and it goes back, it's going to go to this address, 0804921E, and that address is in the main routine. And you can see that if you disassemble main, this is the assembly code that runs the main routine, and here's where it calls test PW. When it's done, it's going to return to here, 0804921E. And that is the number that is stored here on the stack. And this is the fundamental weakness of buffer overflows. Since I'm putting in the capital A's here, I can overflow and change that number. So now let's do the overflow. If I run it again, yes, and now I put in 20 A's. Now here I'm at the breakpoint. Now if I do info registers, the ESP is B0, and this is still C8, and this is the fundamental problem with C. I put in a larger variable, but it did not allocate more memory to store it. It stayed exactly the same size. So now if I examine the stack, and I go from B0 to C8, that's here, and you can see this is, I only made it to here. I didn't overwrite that bit. Now it's going to crash because I corrupted EBP, and that's an unexploitable crash. That's a crash that makes the program stop, but I can't take control of the machine yet. To take control of the machine, I want to get control of EIP, which is here. So I need a few more characters. So let's run it again. And now I'm going to start from the beginning, and I'm going to put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 30 characters. And now I look at the registers, and I see again EBP is C8 still. And now I look at the stack, and now you can see here's the stack frame, and I've now overwritten this with some of those capital A's. So now when I continue, it's going to crash, and this is telling you the address it crashed at, and if you look in the registers, it put that in the EIP. The instruction pointer is pointing to area address 41, 41, 41, 41. And you can see the memory reserved for this program with info proc mapping. I think it's proc mapping. Yeah, this shows you the memory regions reserved for use by this program. And you can see that 41, 41, 41 is not one of them. So it tried to go to some memory that is not available for this process, and that's why it crashes. So we can now exploit it. All you have to do is disassemble win. This is the I want to run this function, so I want to put that in instead of some of those A's. Now, the next step is to figure out which A's did it, so you don't just feed in a long string of A's. You usually do that in fuzz testing, just to see the crash. But when you want to find what characters controlled this crash, you put in something more controlled. Like this, you put in 3, 4, 5, 6, 7, 8, 9, 10, and then something like that. You put in a non-repeating pattern of characters. Now I can do info registers, and I'll see that EBP is still where I expected it to be at 4C8. So if I look at the stack, there it is. And so it's the 45s. That's A, B, C, D, E. The E's controlled the instruction pointer. These 4 bytes here end up in the instruction pointer. And I can prove that if I continue, it's going to crash, but now it crashed at 45, 45, 45, 45. So now I know how to control it. So all I need to do is feed in those bytes. Now the problem is, those are typically non-printable bytes. You can't just type characters that go to those bytes. That's why you need to use a language like Python to send the attack. You just need some way to move arbitrary characters here. So here's this exploit PWD32 should be the script. I should have it ready to go. You get out of here, and nano. There. So here is the attack, and here's how you feed in those bytes. And good, that projector is nice. It makes these faded characters readable. 0804, and this is where. Now you have to go to the right address, and this, by the way, varies on your system. So let me go back in and make sure I know the right address for the win function. If I go into here and I disassemble win, it's here. That is the address I want to go to. So I copy that, and now I check that, make sure it's right here. It is, okay, good. So that's the address I want, and this is the part that gets annoying. Because it's little endian, strings go in byte by byte in order, but numbers go in the other way. So this address has to be put in reverse order. You have to put in D4 910408 in a string. So that's what I put in enough characters before to hit the magic 4 bytes. I put in these 4 bytes. And then, by the way, this is a best practice in exploit development. Always insert the same total length, because a different length might crash for a different reason, like I showed you. When I put in 20 characters, it crashed, but not for the same reason as when I put in 30 characters. So if you don't want to go mad, always keep the total length fixed when developing the exploit, or you will sometimes be hitting one error and sometimes hitting another error and lose track. So I filled this in just to keep the length fixed. So this magic string, which is not printable, when fed in, we'll do it. Now, so I'm going to put that in a file. That is, this program is exploit PW32. If I run it, it prints on the screen, and you can see it's going up the alphabet, but something happened around here where there aren't 4 characters. There were some unprintable characters in there. And so what I do is I put that in a file, like foo, and then to examine the contents of a file that includes unprintable bytes, that's what you use XXD for. XXD prints out this thing like you see it in Wireshark, where you have ASCII, and see here's the 4 unprintable characters, and here you can see what they are, 080491D4. This is how you can examine a binary file easily in command line Linux. So now I have it in the file, so I can just run PWD32, and I can take the input from foo. And now I get you win, because it took the input from this file, which contains the magic characters that cause it to change the instruction pointer to point to the uwin routine, and then it crashes because I destroyed the EBP. I wanted to make an exploit that wouldn't crash it. I would also have to make these 4 bytes have the correct value to maintain the EBP. So it can't return from main back to the operating system without crashing. But I do get to run the code the developer didn't want me to code, and that's the simplest case of a buffer overflow. This, by the way, is not the way it all started, is the one we're going to do later, where you actually inject code and run the code you injected. That was the classic Alex Null's type, but that one has been pretty much prevented with data execution prevention. So this less powerful exploit is the one that's mostly used now, called return-oriented programming. Since you can't inject code and execute it, you reuse code that the developer put there for an unintended purpose. That's return-oriented programming. You take the code that's there and take little pieces of it and patch together your exploit, like making a blackmail letter by cutting words out of the newspaper. Because you can't inject any new code, you just repurpose the existing code. And that's what this is doing. I didn't inject any new code, I just ran code that was there, but I did it when the developer didn't want me to run it. Yeah? Yes, if the randomizing is on, then you can't find the code, and the solution there is incredibly simple. You find some code that's not randomized, and it turns out that not all the code is randomized. Some of the Windows libraries and some other, for one thing, legacy code written before this became popular, cannot be randomized. It's compiled without that option. So if they're running any old code, it won't randomize, and there are parts of the operating system that don't randomize. So that's what you do. You're right, something has to be, there's another thing too. This is what happened in Windows Vista. The early version of randomization was not very good. There were only 8 bits of random. So all you have to do, is run your exploit 300 times. You have 1 chance in 256 of it not moving. So you have to, you're right, the randomization would prevent it, but those are how you get around it. And typically the second one is the powerful one. You find some code that's not randomizing. And it turns out there's plenty of code that's not randomizing, even in a modern Windows system. If they randomized everything, then all your exploits would become much more difficult. Or you'd have to find high-level exploits, like SQL injection and command injection, that aren't at this binary level. But there's a very good point. And there's always a defense, and there's always a new attack that punches through the defense. It will never stop. Good. Anyway, so that's one to try here. That'll get you started.